Next up is example 6, where we will use transformation technique for the continuous random variable and find the distribution of new random variable y. So let's read the example. So let x has the exponential distribution with mean 1. Let's find the distribution of y, which is defined as square root of x. Okay. So before we dig in, let's write down what we know from this given example. So x follows exponential distribution of mean 1. I'm going to go with scale parameterization, which is in terms of beta. So since beta is the mean for the scale parameterization of exponential distribution, since it says mean 1, so beta is 1, and we know the density function for this particular exponential distribution is e to the minus x for x greater than 0. I'm going to just skip the range where f of x being 0. And what we need is we want to find the density function of y, okay, which is denoted as f sub y of y, right? So before we apply transformation technique, we need to check several one conditions whether these g of x, y, square root of x, which is g of x, is monotone over its the support of x. Is square root of monotone? Yes. G of x is defined on the positive side of x, and it is monotone. So it's checked. So by the theorem, one that we just stated, the density of y is obtained by plugging in inverse of g of x multiplied by absolute value of derivative of inverse of g, which I'm gonna find in a second. So I'm gonna write each ingredient on the right side. So we know y is g of x is y equals g of x is square root of x. Solving it for x, we get x equals to y squared, and the dy of this inverse function. By the way, y squared itself is now one-to-one function, but we are restricting the range for x for the positive side, so inverse function is valid only for the positive side. But anyways, the derivative of y squared with respect to y is 2y, so these two are the ingredients we need. Okay, so time to dig in. So our density function of x is e to the minus x, but instead of x, we are going to replace it by the inverse of g, which is y squared, and multiplied by absolute value of 2y. So if you just clean it up, 2y e to the y squared. Okay, this is not the end, because when it comes to defining the density function for random variable, what we really need to be careful is the support of the given random variable, right? So for x, we know support of x is the positive values of x, right? In this case, what is the possible value of y? So y is square root of x, and whenever x is positive, y is positive, so it gives us natural support for y on the positive interval. So well, I'm just stating the same. So distribution of y is indeed given as 2y times y squared for y greater than 0 and 0 outside of the positive interval. Okay. Do we have any name for this random variable? Have you ever seen a density looking like that? To me, not really. So far, among the named distribution we discussed in class, I don't have any particular distribution with density looking like this. So I'm gonna leave y defined as it is, and that is the end of this example.